Dr. Songe, Professor in Mechanical Engineering Department. I will be talking on reversed carnot cycle. Before directly starting to discuss about reversed carnot cycle, first let us discuss about carnot cycle. I have presented here a carnot cycle on temperature versus entropy chart. I am not discussing much about the property, thermodynamic property, entropy here, because already in applied thermodynamics you have studied it in detail. So Carnot cycle is plotted on temperature versus entropy chart. The Carnot cycle, on this chart there are 4 states, thermodynamic states. State 1, state 2, 3, 4. So these 4 states and this cycle, it comprises 4 thermodynamic processes. When there is a change of state, then we call that as a process. So in this, state 1 changes from 1 to 2. So that's why 1 to 2, it is a process. So like this, in this cycle, there are 4 processes. From any state you start, you will end at the same state. So that's why it is called as a cycle. So from state 1 if you start, 1 to 2 to 3 to 4 to again 1. So that's means initial state and the final state, they are same. So that's why this is called as cycle. So this cycle consists of 4 processes. Process 1 to 2 is isothermal process. That means temperature remains constant. And in this process, if you observe, the entropy, it increases from state 1 to state 2. So entropy increases and temperature remains constant. So in this, the heat transfer, heat is added into this process. So as this is the heat addition process, the entropy will increase and the temperature remains constant. So that's why process 1 to 2 is called as isothermal process. Next process, that is a 2 to 3 process. 2 to 3 process, it is isentropic process. That means entropy at state 2 is equal to the entropy at state 3. S2 is equal to S3. So this process is also called as reversible adiabatic process. In this, entropy remains constant and temperature reduces. That means in this process work is developed, work is going out. So this particular process is called as reversible adiabatic process. Heat transfer 0 and entropy constant. Then the process 3 to 4 is again the isothermal process. But in this process, entropy reduces. If you compare the process 1 to 2, entropy increases, and in process 3 to 4, entropy reduces, keeping the temperature constant. Entropy reduces, that means the degree of disorder is reducing. When the degree of disorder is reduced, that indicates that there is a decrease in entropy, and the same is indicated in the process 3 to 4. So that's why process 3 to 4 is again isothermal heat rejection process, because heat is rejected in this process, and due to rejection of heat, entropy reduces. Process 4 to 1 is the constant entropy process. It's also called as adiabatic, reversible adiabatic process or isentropic process. In the process 4 to 1, again the temperature increases. That means temperature increases and entropy remains constant. That means we are providing in this work input. So this is the isentropic pumping or compression process. So like this is the Carnot cycle. It comprises two isothermal processes and two reversible adiabatic processes. Now let us see in which equipment these processes are carried out. Now these are the four processes. So four processes are carried out in four devices. Now if process 1 to 2, if I will consider this process, it is a heat addition, that means it is a boiling process. So this process 1 to 2, it is carried out in a boiler. And the process 2 to 3, it is a reversible adiabatic process, and temperature is reducing, so process 2 to 3, it is carried out in a turbine. And process 3 to 4, entropy is reducing, so this is carried out in a condenser. And process 4 to 1, temperature is increasing, so this process is carried out in pump or compressor. That means in short, this is a boiler, then this is a turbine, then this is a condenser, and then this is a pump. So these all processes, these all devices, they are connected to give a net work output. That means boiler produces a steam, that steam is supplied to the turbine, turbine produces a mechanical power, and then that steam is passed over a condenser, and condenser, it cools that steam to the water, and that water is again pumped back to the boiler. So like this power, this cycle, it works. So we can call it as a ideal power cycle also, because in this work is developed and net work is developed at the cost of heat supplied in the boiler. So this Carnot cycle, it is called as a ideal cycle. Why it is ideal cycle? Because all the processes in this cycle, they are ideal processes. Ideal processes means what? They are the reversible processes. That means all the processes, process 1 to 2, 2 to 3, 3 to 4, and 4 to 1, these are the reversible processes. So that's why this cycle is also called as reversible cycle. Why? Because this is a reversible process and all the processes are reversible, so that's why cycle, it becomes reversible. And reversible cycles, they are the ideal cycles. So that's why Carnot cycle is a ideal cycle. So this is a forward Carnot cycle. That means this cycle is operated in clockwise direction to produce the work done. So that's why this is called as a Carnot cycle. Now we are interested in reversed Carnot cycle. So before that, let us see what is a refrigerator. Refrigerator is a device which produces a temperature less than atmospheric temperature. Now this refrigerator, it consumes the work, that is electricity, it consumes the work, that this work you are supplying to the compressor. And that compressor, this refrigerator, out of which compressor is a one component. So this refrigerator, it pumps the heat from low temperature reservoir to the high temperature reservoir. And in this area, a low temperature is created. So in short, if you apply the first law of thermodynamics, then work is supplied, heat is taken out from low temperature reservoir, and work and the heat taken out from low temperature reservoir both are thrown into the atmosphere. So QH is equal to QL plus W work done. So like this refrigerator, it produces a low temperature in the refrigerated space at the cost of electric consumption. So this is about the refrigerator. Now this refrigerator we are running on a reversed carnot cycle. We discussed about the carnot cycle. Let us discuss about the reversed carnot cycle. So reversed carnot cycle, here on the TS chart, that is a temperature versus entropy chart, it is drawn here. Now in this, the cycle is operated in anti-clockwise direction. In carnot cycle, we used to operate the cycle in clockwise direction. So here anti-clockwise direction, we are operating it. If I will start from the state 1 to 2, it is isentropic process, isentropic compression process, because in this entropy remains constant and the temperature increases. This process is also called as reversible adiabatic process. 2 to 3 is isothermal process and 3 to 4 is again isentropic expansion process. In process 2 to 3, the heat is rejected. The arrowhead, it is shown outward, that means heat is rejected. And 3 to 4, it is an expansion process, isentropic expansion process. And 4 to 1 is the heat addition process, that is constant temperature heat addition process. So in this process, 4 to 1 process, heat is taken out from the space which is to be refrigerated, from the space whose temperature is to be reduced. In this cycle, if you take a working substance, is say assume freon gas is a working substance. So this freon gas, it is circulated in the cycle. Say. Now from process 1 to 2, the freon gas, it is a compressed isentropically and its temperature is increased. And in the process 2 to 3, the high temperature gas rejects its heat to the atmosphere and the high temperature gas gets cooled. And 3 to 4, in the expansion device, the pressure is reduced and the temperature also reduced, keeping the entropy constant. So this is a 3 to 4 process, expansion process, and 4 to 1 is the evaporation process, in which the heat is taken out from the refrigerated space and supplied to the refrigerant which is flowing through the cycle. And that refrigerant, it gets converted from liquid to vapor, and it sucks or it accepts the heat from refrigerated space. So like this reversed carnot cycle, it operates. So in this reversed carnot cycle, you are supplying the work done and you are producing the net effect, that is the Q2. So the process 1 to 2 is carried out in a compressor, 2 to 3 it is carried out in a condenser, 3 to 4 it is carried out in an expansion device, expansion valve, or it is also called as a capillary tube. And 4 to 1 process, it is carried out in the evaporator. So this evaporator coil, it is wound around the space to be refrigerated. So if you take a domestic refrigerator, in the domestic refrigerator, the cabinet where we are putting the food items. So around that cabinet, the evaporator coil, it is a wound. So that is, we used to call it as the refrigerator. At the back side of the refrigerator, there is a condenser, a fine small tube you can observe, and that is called as the condenser. So through that condenser, heat is rejected to the atmosphere, and through the evaporator coils, the heat is accepted, and this compressor, it compresses the vapor refrigerant to the high pressure refrigerant, high temperature and high pressure refrigerant, and that in next it will go to condenser in which it is cooled. The same diagram, that is plotted on PV chart, pressure versus volume chart. So this is a temperature versus entropy chart. Now let us see how the performances of these carnot refrigerators, these are evaluated. Generally, performance of engines, they are worked out using the term efficiency. So for the engine, we can define the efficiency, that is output divided by input. That means output power developed divided by input heat supply. So that is the term which indicates the performance of the engine. But in case of refrigerators, a term, that is a coefficient of performance, is used to indicate the performance. So what is the coefficient of performance? It is defined as desired output divided by required input. So in case of a refrigerator, what is the desired output? That is a cooling effect. So cooling effect, how much cooling effect it is developed into the room, that is the cooling effect. So cooling effect divided by work input. That means the numerator is the output and denominator it is the input. So this is a effect, that means it is a heat divided by work. Both are having the units watt only. So that is, these are the sort of energies. So this QL is the net refrigerating effect divided by work input. So this is about the coefficient of performance of refrigerator. Similarly, coefficient of performance of heat pump can be defined. Before going, what is the heat pump? Heat pump is the device which pumps the heat from low temperature to high temperature. That means if I will take an example of Solapur. In Solapur, the atmospheric temperature, it generally used to be in the range of 30 to 45. But for human comfort, we require the temperature somewhere between 20 to 25. So that means in the room where I am residing, so in that room I must reduce the temperature than the atmosphere. So that temperature reduction than the atmosphere, it is done by the refrigeration system. That means in Solapur, I will use this cycle as a refrigeration cycle, and in this the net effect is how much heat is taken out from the room. That is the net effect, how much heat is taken out from the room. However, if I will take an example of Jammu and Kashmir, in Jammu and Kashmir, the temperature, outside temperature, that is atmospheric temperature, it generally used to be in the range of 0 degrees Celsius. So for human being, the comfort temperature is somewhere around 20 to 25 degrees Celsius. In the room in which I am residing, there I want a temperature 20 to 25, but the outside temperature is at 0 degrees Celsius. That means in this case, I must pump the heat from atmospheric temperature, that is a 0 degrees Celsius, to the room which is to be maintained at 20 degrees Celsius. That means in Jammu and Kashmir, the same cycle, it is used as a heat pump, and while in Solapur, the same cycle is used as a refrigeration system. So this is the difference between refrigerator and the heat pump. So that means in the refrigerator, the net effect is how much heat is taken out from the room, and in case of a heat pump, how much heat is thrown into the room so that the room temperature will be higher than the atmosphere. So this is the difference between refrigerator and the heat pump. So on the same ground, the coefficient of performance of heat pump, it is a desired effect, desired output divided by required input. The formula for the refrigerator and for heat pump is the same, but only the numerator, it is a different. In case of a refrigerator, the numerator is a cooling effect, that is a desired effect, and in case of a heat pump, there is a heating effect, that is a desired effect. So that is a QL divided by W net, and for coefficient of performance of heat pump, there is a QH divided by W net. So like this, the performance of the carnot refrigerator, they can be compared by using the terms coefficient of performance. Sometimes we cannot measure the net effect, cooling effect, there is a heat and the work. So in that case, we used to know only the temperatures. So if the temperature of the atmosphere and the temperature of the room, if we are knowing, then from the temperatures only we can calculate the coefficient of performance of Carnot's refrigerator. So Carnot's refrigerator coefficient of performance is defined as lower temperature divided by temperature difference between atmosphere and the lower temperature. That is a room temperature. Because in the room we are going to create a low temperature. So room, in short, in another language I can say lower temperature, that is a room temperature, divided by temperature difference between room and the atmosphere, that is the coefficient of performance of Carnot's refrigerator. And similarly, Carnot's heat pump is the COP of Carnot's heat pump. It is defined as higher temperature divided by the temperature difference between higher and the lower reservoirs. So in this case, the TH is the temperature of room and TH minus TL is the temperature difference between room and the atmospheric temperature. So the lower term, it is the same. There is a denominator term for Carnot's refrigerator and the heat pump. It is the same. Only the numerator term it changes. So if you will analyze this, then I can conclude from these relations that Carnot's the COP of heat pump is equal to 1 plus COP of Carnot's refrigerator. So like this, we discussed about the Carnot's refrigerator, heat pump, and Carnot's cycle and coefficient of performance. Thank you.